bear with us, all of us, me too. I have been stuck in the house for 1.5 months already. And as I said, I didn't even go out anywhere. The farthest I went is the driveway, and that's all, to look at some beautiful roses in the front of my house, and that's it, and then come back. So hopefully you, I know 1.5 months is a long time, but we are almost at the end already. So okay, so I tried to wait for a few more students, but now it's 1:33 already. So let me start the lecture anyway. So last time we talked about fixed point and floating point arithmetic. So I know now you know what fixed points, what a fixed point is, right? So and today we will learn about floating point too. So in 2 more lectures, basically you know exactly how to represent a real number using binary digits. Okay, so let's review. Let's see what we learned last time. Let me ask you a few questions. For example, in this case, right? So in this case, assume that we have 8 bits only. So 100100011, right? Of course, when you store this binary pattern in a register, for example, there will be no radix point, right? No bits is reserved for the radix point. It is only the implicit radix point for the programmer, right? So if we are a programmer, and I told you I will use the format 4 dot, this is a sign, 4.3, right? Then you have to understand that this 8-bit binary pattern we have 3 digits after the radix point. Okay, so just implicit, but actually in the register we don't really represent the radix point at all. Okay, so now to test your understanding from the previous lecture, let's say just assume, okay, just assume. Let's assume that the binary patterns in the register is the same, 100100011. Okay, and I tell you I'm using my program using fixed point representation with the format Q 3/4, 3.4. Okay, 3.4. So basically 4 binary digits to represent the fraction. Okay, so what is the real number this binary pattern represent? Can you calculate quickly for me? Instead of Q4.3, I'm using Q3.4. Okay, so what do you think? Yeah, please respond to me. I'm waiting for your answer before I proceed with my lecture. Go ahead. Okay, Kristen said decimal a little bit closer to 1. Yeah, but go ahead to tell me the whole real number it represents. Okay. So what is the real number that this binary pattern represents? 100100011. Assume that the format that we are using is Q3.4. Okay, quickly. Wow, I see a correct answer coming in. Twin, thank you so much. Do you understand what Twin just type? Minus 6.8125. Excellent number, Rizzo. Do you understand what she said? What she typed? Hopefully everybody understand that result. If not, let me repeat again. So yeah. So the way you calculate the real value is you use this formula, right? So just forget about the radius point over here. The IA is the integer representation of that floating point. Okay, so the integer representation is the 100100011. Just forget about the radius point and assume it is a integer. So what is that thing? What is that number represent? It represents minus 109. Is that right? This binary pattern in 2's complement, it represents minus 109. Okay, minus 109. Okay, and then because I just told you, I use the format 3.4. So now n here is actually 4, right? So the real number is you have to divide the integer representation by 2 to the 4th, meaning you have to divide by 16. So if you divide it by 16, you will get minus 6.8125 as twin just answered. Understand, everybody? So now you know what is the integer representation of a fixed point. Okay, this is the integer representation over here, and in this case, this is minus 109. Okay, understand? Okay, let's move on then, right? So last time we talked about. Oh, by the way, let me see. Let me see over here. Okay, I just want to remind you for the final exam, please be very efficient to convert between the fixed point to fixed point representation, right? To binary over here, right? And then change it back. So 2 direction. You really have to know how to do that very quickly. Okay. And I even asked you to change a floating point, a real number represented by a fixed point number to a floating point that we will learn today. So know all of that. Like last time in chapter 2, I asked you to change between what? I mean, I forgot, but I mean from binary to integers, and then from integer back to binary, right? And with both positive and negative number. So you have to be prepared for that, change back and forth. I think that doing homework probably will help you as well. Okay, so now after knowing what fixed point numbers are, we actually start to talk about operations on these fixed point numbers, right? So it seemed to me last time addition and subtraction seem to be easy for us, right? So if you have 2 floating point number, FA and FB, right? And each of them, of course, I mean, FA is represented by integer pattern IA, right? And then FB is represented by an integer pattern IB, for example, right? So how to calculate the sum over here? It's turned out to be very simple. If you have FA and FB, so the integer representation for the sum I see over here, it's just equal to the integer representation of A plus the integer representation of B. Very simple, right? So it means that when you try to do the fixed point operation, you can use the regular add and sub instructions to add them as normal, and then only at the end you can take the representation and change back to real number if you want to, right? But when you are doing operation, just pretend them, and actually in C, you just represent the fixed point here, declare them as an integer actually. Okay, so very simple over here. Okay, so now the question, of course, I mean, okay, so the question is, how about multiplication and division. What do you think? What do you think? So if you have a fixed point number FA and a fixed point number FB, right? And if you multiply them to get the fixed point number FC, do you think that the integer representation of the product will be equal to the integer representation of A multiply the integer representation of B? What do you think? Yes or no? Is as simple as this? IC equal to IA multiplied by IB, do you think? Please go ahead and answer me. Oh, Jake answer yes. Anybody else? Yeah, please. Probably. Okay. Any more responses? I'm waiting. Okay. The answer is not that simple. Okay. I have this. It's actually the answer is no. You have to do something a little bit special. Do you know what? The reason is this. Okay, so let me tell you. For example, just the thing about decimal. Okay, so for example, if you multiply 1.1, okay, with 1.1, right? If you multiply two real numbers and each real numbers has one digit after the decimal point, okay? So do you agree that the product will have two digits after the decimal point? Do you agree with me, right? For example, if you multiply 1.1 with 1.1, for example, then you will get 1.21, right? So you have two digits after the decimal point, okay? But remember, for fixed point, we always assume a fixed number of digits after the decimal point, or in this case, after the binary point, right? So you are allowed to keep only one, right? So that's why you have to chop off one of the digits after the decimal point, right? Understand? Okay. So let me repeat again. And this one I will ask you. Okay. If you have two real decimal numbers, okay, the first one has 16 digits after the decimal point. Okay, the second number also has 16 digits after the decimal points. Now I multiply them together. Okay, how many digits after the decimal point will the product has? Please answer my question. Matthew said 32. Anybody? Please. Jake also 32. Yes, that's correct, right? That's correct. This is I don't know. Maybe you learned multiplication from what? From junior high, or even I don't know, even the elementary school, right? So yeah, you will have 32 digits after the decimal point. But I tell you that, okay, I only have 16 spaces after the decimal point. That's why you have to chop off 16 digit, right? To keep only 16 after the decimal point. Understand? Just chop it up. Okay? So for fixed point, it's a very similar situation over here. So let's go to the next slide and you will see. Okay? So if I have a fixed point A and a fixed point B, right? Fixed point A, of course, is represented by the integer number IA, and then FB is represented by IB over here. So we are asking what will be we are trying to find FC, right? Based on IA and IB, of course, right? We try to, and then we also say that for FC, we just keep only 16 bits after the binary point. Okay, so if you do this multiplication over here, right, and you will see that the binary, the integer representation of IC is not simple as IA multiplied with IB, but it also has these things. See that thing? So IC equal to IA multiplied with IB, and also multiplied to 2 to the minus 16. Okay, 2 to the minus 16 is similar to IA multiplied IB divided by 2 to the 16. Okay, you understand what I'm saying, right? So, so the IC, to get the IC representation, just IC, not the fixed point yet, right? To get the IC, to get the correct IC over here, after multiply IA with IB, you have to shift the result right by 16-bit. Basically, you chop off over here. Okay. So now let's look at over here, and you will see. For example, if I have two fixed point, the first fixed point is A. Okay, and it represented by this format, either is 16.16 or 15.16 for the side fixed point number. Okay, so from here you will see that 16 of them, 16 digits, are after the binary point. Okay, so this is a fraction over here, and this is a fraction over here, right? And the integer representation for FA is a whole 32-bit over here, right? And the integer representation for B is the whole 32-bit over here, right? So when you multiply, just assume, forget about the decimal point for now, okay? Let's take this integer IA and multiply with the integer IB, 32-bit here, multiply 32-bit here, right? So then you have to prepare 64 bits for the product, right? Is that right? So this is the whole, from here to here is 64 bits for the product over here, right? Okay, 64 over here. So that's why we need to use, okay. Yeah, that's why we need to use two registers to store the product. I use R3 and R2, okay? R3 has 32 bits, R2 has 32 bits, right? So you can see if you multiply these two integers together, right? Basically, IA multiplied by IB, you will get everything over here, right? But remember that to get the integer representation for IC, you have to shift the product here to the right by 16 bits, meaning you just chop off, discard these 16 bits, right? Because from here to here is actually 32 bits fraction of the product, right? So just chop it off for me, chop it off 16 bits over here, meaning shift to the right by 16, okay? And you also, remember, IC, I tell you, we have room only for 32 bits. So you also need to chop off 16 bit up here too, right? Because if you have some bit up over here, they should be 0. If they are not 0, meaning the product is overflow. So in that case, the hardware will tell you it's an overflow, right? So so basically, for your application, you know that you have to pick the fixed point range so that you don't have overflow case. So in this case, they are 0 up here too. So you just chop off that thing for me, right? So the real result for FC is you take the 16 least significant bit of R3, right? And you concatenate with 16 bits, 16 most significant bit of R2. So that's how you construct the IC. Understand? Okay. So let me move to the next slide. Maybe hopefully it will be a little bit clearer, right? So as I said, we have to. This is your real product over here. This is actually your IC, okay? So basically, you have to take the least significant bit of R3, okay? Concatenate with the most significant 16 bits of R2. Just remember that, okay? So move to here, move to the next page over here. Okay, so this is R3, okay? This is R3, 32 bit over here, right? So 32 bit of R3. So basically R3 is over here, right? So let me move this 16 bit from here to here. Is that okay? Let me move this CH over here from here to this half, the upper half. Okay? Okay? And then I move C low over here, right? From the most significant half to the least significant half over here. Okay? So let me move this one to there. Let me move this one to here. Okay? So you can see over this is a R3 over here, right? So let me move the C high from here to there. Okay? And for R2, let me move the most significant 16 bit from this half to this half. Okay? And then I OR these two registers together. I OR R3 and R2 and put the result in R4. So you can see when you OR this one with 0, you will get C low over here. And when we OR this one with this 0, you get C high over here. Okay? So if you look at R4, it is exactly this result over here. Do you understand, everybody? Okay? So that's how you construct IC, the product here, right? And put it in R4. Okay? So R4 is R4 represent the fixed point number of FA and multiply with FB. Okay, understand? Okay, so if you really look at the code, the assembly code, you will see that we are doing exactly these steps. Okay, understand? So okay, so look at over here. So for R0, we have 32 bits over here, right? And remember that 16 bits are for fraction. Okay. Similarly, for R1, we use R1 to store the fixed point number B. Okay. And remember that it also have 16 bits fraction over here. Okay. So now we try to multiply A and B and put the result in R4. Remember the way that we construct R4, right, to represent the FC, okay? So first of all, right, assume they are integers, right? Just integer. So you use the unsigned, because this is unsigned over here, okay? So you use unsigned multiplying, okay, with long. Long means the result will be 64 bits, okay? So R0 is 32 bits, R1 is 32 bits, and the result will be 64 bits, and it will be put into two registers, R2 and R3. R3 will get the most significant bit. R3 over here will get this part, okay? And R2 will get this part, okay? And now we really have to take the middle part over here and put in R4, and then you're done. Okay, so how to do that? So you can see, so now look at R3 over here. Okay, look at R3. Okay, so you shift left by 16. Okay, so basically you move this half to here. Okay, so for R2, you shift right. Okay, you move this half over here. Okay, then you OR them together. Basically, you pack two halves into a word, you OR them together, and you get R4 over here. This is exactly what we are saying over here. We shift left for R3, so that the 16 bit here will be here. For R2, we shift them right, so that the last, the 16 least significant bit of the product will be here. And then you OR them together and put in R4. So this is R4 is actually the product of A and B. Okay, that's how you do it. Okay, easy, huh? Okay, so now how about for psi? This is for unsigned 16.16, right? So how about for size 15.16? This is exactly the same, except that instead of using unsigned multiplication over here, you use psi multiplication, and that's it, right? So if I move to the next slide over here, you can see the only difference for the fixed point, for psi fixed point number over here, you replace the u with the s, right? Unsigned with the psi over here. Everything else is the same over here. Okay, very good. Okay, so I hope that you understand the fixed point multiplication, fixed point number multiplication. So, a little bit complicated, but not that complicated, right? William, are you?
Just a quick note. Side note, might have want to change up a comment you have for SMULL being unsigned rather than signed. But that's separate.
I see. You mean the comment over here, right?
Yeah.
Oh, that's a typo.
But that could be something else.
Yeah. Let me fix it. And then upload it back to Canvas right after the lecture. Okay. Yeah. Clearly, this is the copy and paste, but they forgot to change the comment. Yeah. Wonderful. Yeah. I will do that. Okay, so now hopefully you are comfortable with that. And now let's look at the division, and that's all, right? So multiplication, you understand. So division is okay, right? So multiplication, if you have 32 bits, you multiply with 32 bits, all right? And then you will have, the product will be 64 bits, right? So now for division, 32 bit divided by 32 bits, I think that maybe before, to be precise, before you do the division, you should change to 64-bit first by psi expansion or something like that, right? So A just change to 64-bit, B change to 64-bit, and when you divide, you get the product. The quotient is 32 bits. Okay, so just have some idea like that before we go to the next slide. So slide number 13. So that will be the division. Okay, so you can see it's not simple as for example, if you do addition, right? So the is IC equal to IB plus, IC equal to IA plus IB. So that's for addition or subtraction. Okay, but for division, the difference is just this guy, right? So it's not IC equal to IA divided by IB anymore, but you should have this one. And it's easy. If you follow this calculation, you will see, right? So if you follow over here, you will see if you divide this one by this one, right? You will have a factor of 2 to the 16 over here, okay? So the integer representation of the quotient, to find that thing, first of all, you use the integer representation of A, right? And then you shift what? You should shift left, right? Because shift left means multiply. If you shift left by 1, it means that you multiply some number by 2, right? So if you multiply by 2 to the 16, it means that this group here, the product here, will be IA shifted left by 16 position. Is that right? Understand? So before doing the division, you shift IA by 16 to the left first for me. Okay? And then you do the IB, you divide with IB. Okay? So let's look at over here. Okay, let's look at over here. So for example, let me see over here. Okay, so for example, you have a 32 bits to represent a fixed point 16 by 16. or this one, or 15 by 16 over here, right? So this is a fraction over here, 16-bit fraction, and it is in register R0. Okay. So for B number, the fixed point B number, I put in R2. Okay, and it also have 16-bit fraction over here. Of course, in the register, you don't you don't have any bit to represent the radix point. Okay, just 32-bit over here. Just implicit. So now what you want to do is you want to divide R0 by R2, right? So as I said, first of all, just convert it to 64 bits first for the division to be accurate, right? So for R2 over here, I will convert it to 64 bits, right? That's why I use two registers. I use register R3 as well, right? And R3 should be just just store the psi extension of B over here, okay? So basically, even I use 64-bit over here, it just represents the same number as the one in R2, right? Because R3 is just a psi extension of the bit, the psi bit of B over here, right? Over here, just psi. So if the psi bit here is 1, R3 will contain all 1 over here. If the psi bit here is 0, R3 will be all 0 over here. But remember, now I use the B number is actually, I use two registers over here to represent the B number, okay? Now for R0, okay, R0. So R0, this is the 32 bits R0 over here, right? So I like to represent R0 with 64 bit as well. So that's why I use another register R1. Okay. So just forget about the shift over here. Okay. Just forget about the shift. So if I use two registers to represent R0, what do you think? So in that case, A high will be here. Is that right? A high will be here, right? And A low will be here. Is that right? A low will be here. It's like this. B high, B low. So I will have A high and A low over here. And R1, all R1 will be the psi extension of A, right? All R1. So R1 will be 0, 0, or 1, 1, 1, 1, all of them, right? However, okay, you just remember the R2, you just remember the R1 is like another register right here, put in front of R0, okay? So the number A will have 64 bits from here to there, okay? So now, before doing the division, you have to shift that 64-bit A to the left by 16, okay? So you can see A low before is here, right? If you shift 16-bit, it will go from here to there, okay? So A high, before it is here, so now it is shifted back up to here, okay? And then the remaining 16-bit over here will be the psi extension of A. Understand? So this is what you are doing. What basically you prepare the setup before you do the division. Okay. So now this is a 16-bit of the number. 64-bit of number A already shifted to the left by 16 location. Okay. And this is the 64-bit representing number B. Okay. Over here. Okay. So after you prepare that one, okay, in 4 register over here, okay, and you can do the division, okay. The division, we will not talk about 64-bit division because I think that is in chapter 9. Chapter 9 is the chapter that we actually skip, right? So in case if you are interested, you can read by yourself. It's not really hard at all. So just a 64-bit extension, right? So in this case, I just teach you to prepare the 64-bit over here, okay? Then that's it, okay? Then you call a function. You will call a function in chapter 9, okay, to do that division for me. Okay, so your job over here is just to prepare these four registers, okay, and call the function to do the division, 64-bit division. Okay, so let's see. Let's go over here. Okay, this is what you have to prepare. This is just repeat from the previous slide, right? So you will prepare R1 and R0 like this, and you will prepare R3 and R2 like this, and then call a function. Okay, so you can see over here, R0 is fixed point number for A. R2 is a fixed point number for B. Okay, so now I would like R4. I would like R4 to contains the quotient, right? The quotient for A divided by B. So how do I do that? So over here you can see. So first of all, I convert the 32-bit R0 over here to a 64-bit, right? And also shift by 16, right? So you can see. So first of all, let me see R0. Okay, R0 shift by 16, right? R0 shift by 16. So it will be here. Is that right? R0 shift by 16. So A low will go up to here, okay? And you put this result in R1, okay? Then R0 you shift. Oh, this you shift. Oh, I'm sorry. Let me. This is a shift right. I'm sorry. This is shift right over here. Okay. So first of all, you start from here. Okay. I overlooked this is a shift right, not shift left. So you start from 32-bit over here. Okay. You shift right. You shift to the right. So these 16-bit will be gone. Is that right? These 16-bits will be gone. Okay. And these bit will store the side extension of A high. So you will get something like this, right? Remember, this is a arithmetic shift, right? So it will replicate the side bit for you. So when you do this, you will have something like this, okay? And you assign that shift result to R1, okay? So the first instruction over here, create this R1 register for you. Wonderful. That's exactly what we want, right? Okay, so now the second instruction over here, we like to create R0 like this from this, right? So basically you just take the R0, the old R0 over here, shift left by 16, right? So this one will go over here and override the high part of it, okay? And these are 0, right? Like this. Okay, so if you shift left by 16, you will get something like that. And you just assign back to R0 again. So this is exactly what it is. You take R0, shift left by 16, and put back the result in R0. So you have this one. So from the first two instructions, you have prepared R0 and R1 like this. Excellent, exactly what we want. Okay, so now you have to prepare these register, okay, for number B. So how do you do that? So that's a very example. It's simple. You just take. So basically, R2 is the same R2. You don't need to change anything, right? So this is behind. This is behind. This one below. This is below. So we don't change R2. The only thing is we use R3 with the side extension. So that's what you just say. Take the R2 and do the arithmetic shift, right? So you can see when you do this one, you will create the result of 32 bits, just the side bit of R2, right? And then you put that 32 side bit in R3, and you will get this one, okay? Now, you already learned in chapter 8, right? How to call a function. Remember that now you have to call a function to do the 64-bit division over here. So this is the BL, right? This is the branch and link, right? and call this function. We don't study the function here, but we just say that, assume that this function division 64 bits is available. So you just call them. So before calling this function, you just pass the argument for me. And the argument are four register, each register 32-bit. So R0, R1, R2, R3. So you prepare that, you put it over here, right? You call the function, okay? So after calling the function, remember the function will put the result in a 32-bit quotient in R0, right? So, but we require that I like to put the result in R4. So that's why you just move the return value from the function from R0 to R4. And that's it, okay? Okay. So do you understand the assembly code over here? Okay, so with that,
the move is just so that way we could just leave, change the spot of the register, and instead of having to stick it in register 4, we can just move it back to R0 since we don't need R0 anymore. All right.
Oh, I don't know. This is just a portion of a bigger program, right? So in this case, after the function call over here, the function will put the quotient in R0. Okay. Okay.
Yeah, because I was thinking the bare minimum was the first 4 lines. The 5th line is just so that way, if we want to lower our registers, we could just overwrite the R0. That's why we do it that way.
I don't know why we have to move from R0 to R4, right? But it is because this is just a very small portion of a bigger program. So maybe down here, maybe they want that result in R4 to do next calculation, right? We don't care, because the requirement here is they just say, please put the quotient in R4. Okay, so we should try to do just follow what they request over here. Maybe meaning putting the quotient in R4. So that's why this step is just to do this, and that's all. And I don't know the purpose, because we don't know what is the remaining of the program over here, right? But that's nothing. This point is a very likely point. If you don't want to move the result to some anywhere else, just leave it in R0, right? It doesn't matter. Okay.
Okay, I was just curious about line 5 in that regard, because
yeah. Well, that's because they want to put the result in R4. Okay. How about this one? In the final exam, for example, if I ask you, please put the result in R12, then this one will be moved R0 to R12. Okay. So
yeah, because
that question
we didn't have move for the multiplication, so that was the ever distinctly different process of it as well.
Okay. Okay. So with that, I hope that you understand all about fixed point number. So now the remaining thing is just practice for me. Okay. Practice. Changing back between the real number to the fixed point representation, or change it back. For example, I ask you, I have a real number, 15.2, for example. And please change that into the fixed point representation, 8 bits, for example, in the unsigned format, with 4 bits represent the fraction, for example. Then you have to know how to do that. Okay, change back and forth. I hope that I didn't really look at the homework, but I hope that in the homework we have several questions for you to practice that. Okay, so let's move to another very, very important area for the real number representation. This is very important. That's the floating point. Okay, floating point. So you know that life is not that simple that we can always use fixed point, right? It's great if we can just use fixed point, but actually it's not enough. Okay, because some application, the range they require, the range is very large range. For example, in your computer, I believe they use 64 bits floating point number. Even for in your laptop, is already we already need that high range for scientific application. Okay, so fixed point is nice, less energy consumption, fast, but it is appropriate only for some applications. Okay, for example, digital signal processing, for example, especially for image processing, the range is not that large at all. I think that later on you will see that they just represent something -1 to +1. I mean, in that range. You know what? Not precisely, but I said roughly maybe from -1 to +1. So it's a very small range. So in that case, fixed point number is a very, very good representation for you to use to speed up the calculation and also to reduce the energy consumption. Okay. So now, but for other application, we have to use a floating point. So what is a floating point? Okay, so let's learn about it. Floating point number. Okay. So now let's look at over here. Okay, look at over here. Let me see. Assume that you have a real number. Assume that you have a real number. 1.75 minus 1.75 multiply with the 2 to the power of -5. Okay, so this -5 is called a true exponent, and this one is a side bit of that one, right? This is the fraction over here, and later on you will see this is called a hidden bit. Okay, so don't worry for now. Okay, this is a normalization format. Okay, normalization format. So what is a normalization format? Normalization format means you only have one digit before the radix point. Okay, you cannot have more than that. Okay, so for example, with this same number, right? With this same number, I can write minus 17.5, right? Multiply with the 2 to the -6. It is equivalent. Is that right? It is equivalent, right? Minus 17.5 multiply with 2 to the -6. Is that right? The number that I just tell you is equivalent to this number, right? Right. However, it is that 17.5 something is not in the normalization form, right? So, for example, in over here, so if you have 10.746 multiplied with the 2 to the 6, it seems very, very similar to this format, right? But if you look at it carefully, you will see that this number over here is not in the normalization format because there is why to store this number in the 32 bits register, right, using the floating point format, you first of all you have to chain it into the normalization first. Okay, so over here, look at it over here and how to chain it. Okay, don't be, if it's a decimal, then it's easy, right? So if you want to move the floating point from here to here, that's easy. You just divide it by 10, right? But remember, this is base 2. So don't make mistake over here in the final exam, okay? Please pay attention, okay? So your original number is here, okay? Now, how to change this number into the normalization form, okay? You see that 2 digit over here, right? So you really have to make the 10 over here to have only one digit before the radix point, And even more than that, that digit has to be 1. Okay, that digit had to be 1. Okay, so how to do that? Okay, so you can see that. Okay, so you take the 10. Okay, you divide it by, remember, divide it by multiple power of 2. So either you divide it by 2, divided by 4, divided by 8, 16, 32, 64, whatever, right? You divide such that the number, the only number before the radius point is 1. Okay, so you can see right away, right? You can see right away. So you have 10, and if you want to become 1, right, you have to divide it by 8, right? If you divide it by 4, probably you will have 2.5 or something like that, right? Or if you divide it by 2, you will have 5 point something, right? We like to have 1 point something, not 2 point something or 5 point something. So that's why you know that we have to divide it by 8, okay? And to keep the number the same, if you divide it by this one by 8, you have to multiply this number by 8 as well, right? To keep the value the same. Is that right? So hopefully, with this one, you are not surprised from here to here, right? A is actually 2 to the 3. And multiply 2 to the 6, then it will become 2 to the 9, okay? And the number over here will become 1.3 something. Really nice. That's exactly the normalization format over here that I want to, okay? So the side bit is positive. In this case, the side bit is 0, and then you have 1 here and dot 3, 4, 3, 2, 5, and then 2 to the 9 over here. Okay, so for this slide, the very first thing that you learn from this one is to change a real number of the real number to the normalization form. Okay, just that, just the purpose of this page, right? For the next page, we will learn how to put this number in the 32-bit register, and you will see at that time you will see that we don't actually put exactly directly number 9 over here, meaning the true exponent, directly into the register at all. You will see that we have to add the true exponent here with some number called bias number. So you will see that we will add with 127 first before you put into the register. Okay, so that's a different. So that's the a little bit different from this slide. Okay, so understand. So to put this number in the 32-bit register, remember that we will do something with this one, not put this one directly. Okay, so how to put into the 32-bit register? Let's move to the next slide. Okay. Okay, so in this case, we have 2 formats. I will teach you only 2 formats. So either it's 32-bit format, okay, or 64-bit format, okay. So maybe about 64-bit format, don't worry about the final exam, right? If anything, I will ask you something 32 bits or less, okay? So this is just for your information over here, okay? So now, how to put this one? How to put this number in this format, okay? So this format is a IEEE Standard 754 format over here, right? So there are 32 bits, right? So we will use bit 31, right? The top bit over here, right? For sign, just 1 bit for sign, right? So if it is positive, as in this case, then we will put 0 over here, okay? Put 0 over here, okay? Now, we will use A bits over here, the next A bit over here, to represent the exponent, okay? But remember, we don't put 9 directly in here. We don't put 9 over here. But before putting the exponent in this A bit, we have to add that 9, I'm sorry, we have to add 9 with 127. Okay. Before you put it over here. Okay. So I would explain to you why people want to do that. Okay. But anyway, the number 9 plus 127 will be what? 136, right? Right. So you change that 136 into an 8-bit binary number, unsigned number, and then you put it over here for me. Understand? Understand? Okay. So now the rest 23 bits over here is for fraction. Okay, it's for fraction. Okay, so look at over here. Look at this this value again. So the fraction is 34325. Is that right? 34325. As I said, for the before storing into the 32 bits, according to the IEEE 754 format, you have to change the real number into the normalization format first. And when you change to the normalization format, you always have a 1 over here, right? So because the 1 is always there, right? So why do we have to store number 1, right? It's always there. We know that the 1 is there. So to save 1 space, 1 bit in the 32-bit, we don't really need to save number 1, okay? We just store 34325, and that's it, okay? So 0.34325 will be stored in these 23 bits, okay? Understand? That's how you represent the number, okay? So look over here. This is the format over here. So how do you? So you just store the side over here, side bit over here. You just store the fraction only, okay? And you store the you store the exponent here, 136 over here, right? But what is the value now in the other reverse direction? If you see a 32 bits using IEEE Standard 754, right? So what is the value of that 32 bits? Okay, so basically going in the reverse direction. So how do you calculate that one? So don't worry, we have example for you to practice on. Okay, so let's move over here. I hope that we can you can understand. Okay, so now for example over here, you have a 32-bit floating point number over here, right? 23-bit over here, 8-bit over here, and 1 over here. So my question, assume this is a final exam question. My question is, what is the real number that this binary pattern represent? That this floating point, IEEE 754 floating point number represent? Do you know? Can you calculate it for me? But before doing that, let me come back here and answer some questions. Let me see. Matthew asked if floating point used in DSP application. Oh, it depends, Matthew. For audio application, it's also DSP. It is used floating point, okay? But for image processing, I think they use fixed point, okay? So Matthew also asked, so it's kind of like scientific notation where your number has to be between 1 and 10. Actually, the digit before the decimal point in the normalization form had to be 1. Okay. Okay. So everybody, please do it. Do this example with me. Okay. Remember that our purpose is to find out the real value of this floating point number. Okay. So first of all, is this the very first question? Is this negative or positive number? Okay. Can you tell me quickly? Type. Negative, exactly. Yeah, because you see a 1 over here. So it is negative, right? Okay, so the next one. What is the true exponent? What is the true exponent of our real number? Okay? Okay. Oh, by the way, this one is unsigned number, okay? We never use 2's complement in the exponent part over here, okay? Never. This is unsigned because for the IEEE 754, if we use unsigned over here, it's very, very fast. For example, if you really want to compare two floating point number, right? So if it's an unsigned over here, it will be very fast. So Kristen said it's a minus 127. So it's actually not correct because this is unsigned. So tell me, if this is an unsigned, then what is this value? Quickly, somebody. 131? Are you sure? Oh yeah. That's right. I remember. Yeah, the way that you change is this is a 1, this is a 2, is 3, right? And this is a 127. Oh, so that's a 130, I think. Oh, I'm sorry. This is a 128. I'm sorry. This is a 128 plus 3. That's a 131. Yeah. Understand everyone? Do you understand that point? So this number is 131. So what is the true exponent? To get the true exponent, remember you have to subtract the bias, right? Exactly. Yeah. 131. Subtract 127 will be 4, right? So you know two information. You know that it is a negative number. The second, you know that the number will be something multiplied with 2 to the power of 4. That's the number. Okay, so now try to figure out the fraction with me. So what is this thing? Okay, so let's move on. So psi equal to 1, exponent 131. That's wonderful, right? And this is a fraction over here. The fraction is a 1, 1, 1, 1, 1, 1, 1. Okay? So let's continue to calculate over here. Okay? So you can see the fraction is like decimal base, right? So if you in decimal 0.1 means that the 1 is divided by basically multiplied by 10 minus 1, right? So in binary, the 1 here is basically represent 1 multiplied by 2 to the minus 1. The next one here represent 1 multiplied 2 minus 2. And blah, 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 blah. Similarly, so if you do this, the fraction here represent 0.9921875. Aha, wonderful. We figured out the fraction, okay? So the result, can I say that the result is minus 0.9921875 multiply 2 to the 4th? Is that correct or not correct? Aha, hit the number. Yes. Don't forget. Because the hit the number, we don't store, right? We know that it is a 1. We don't store. So when we change back, when you get this one, remember to add that one back for me. Okay? So the true number is actually minus 1.9921875 multiplied with 2 to the power of 4. That could be the correct number. Okay, so let's see if that's correct. The fraction here, and you can see the value. Yeah, the value over here, right? The value here is the side bit here, minus 1. You have to, don't forget to add 1 with this fraction, okay? So 1, so that's going to be here, right? And multiply with 2 to the 4. So the number, the real number, this one represents is minus 31.875. Wow, that's a long process, but that's what it is. That's how you convert. Understand? Easy? Now, you know what? Maybe the exam, I will ask you to change back from here. minus 31.875. Back to this representation. Do you think that you can do it? Basically back and forth, okay? Back and forth, something like that. Of course, 32 bits is very complicated. Maybe I reduce the number of bits a little bit, but that's what it is. I mean, as long as you understand the process, then everything will be fine. So let's see if we have any more example over here. Oh yeah, I just tell you, and then we have an example over here. So basically, we change back from a real number and pack it into a 32-bit IEEE 754 number, okay, in the reverse direction. Okay, so now 14.5. How to change this one into this thing? Okay, no problem. Don't worry about it. First of all, is it positive or negative? Positive, right? So this bit had to be 0. The side bit had to be 0. No question about it. Okay. The second, we have to put in the normalization form, meaning 1 point something, right? So over here you have 14, right? So as I told you, we have to divide it by a power of 2, right? So either divided by 2, 4, 8, 16, 32, blah, 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 blah. Divide such that you get a 1. So definitely cannot divide it by 2 because you will get something 7, right? If you divide it by 4, you may get 3 point something, right? But if you divide it by 8, wonderful. If you divide it by 8, then you probably get 1 point something. So divide it by 8 for me, okay? And if you divide it by 8, you have to multiply by 8 for the value to be the same, right? So that's why you can see we have 2 to the third over here, okay? And this is 1.8, wonderful. And 1.8 is actually 1 plus 0.8 something, blah, 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 blah. And remember, you don't really need to store number 1 in this format at all. Just basically, you just care about the side bit, you just care about this fraction, and you just care about the exponent over here, okay? Okay, so do one by one, don't worry, right? First of all, the side, positive, so 0 over here, easy, right? Second, this is the exponent, this is the true exponent, right? But when you put it over here, this is not the true exponent anymore. You have to add with 127 for me, right? So 3 add with 127 is 130, and 130 is actually for unsigned. Yeah, please put it unsigned number in there. Convert it to unsigned binary. It is 10000010, and you just put that one in here for me, right? So we already figured out 9 bits already from here to here. So how about the last 23 bits? So for the last 23 bits, the fraction over here, how do we change to binary? Do you remember in chapter 2 to convert an integer to binary, you divide it by 2, right? You divide it by 2, divided by 2, divided by 2, right? And you will figure out the binary pattern. So in this case, the fraction is actually, you have to multiply by 2, multiply by 2, multiply by 2. This reverse because, why? Because remember, for the fraction, you multiply with negative number over here, right? So that's what to expose the coefficient over here, you actually have to multiply by 2, okay? So in this case, first of all, you take the fraction over here and multiply by 2 for me, okay? So you get 1 point something, and the digit before the radix point represent the first binary number over here, okay? So that will be 1. 1 will go to here for me, okay? Then you will take the remaining fraction, right? Multiply by 2 for me. And if you get something more than 1, that 1 will go to here. And the remaining fraction is 0.25. And you multiply again for me, right? But the digit before the radix point is 0. So that 0 will go to here, okay? And the remaining fraction is still 0.5. And then you multiply by 2 again. And finally, you get 1 over here, okay? And that 1 will go to here. And then the remainder is actually 0. So you stop, right? not remainder, but the fraction is actually 0 over here. So that's why you stop right there. Okay, so you can see the fraction in binary is actually 1, 1, 0, 1, 1, 1, 0, 1. Remaining all 0. Wonderful. Understand, everybody? That's how you convert. So let me see what is the on. Okay, 23, 24. Okay, okay, so we have a few minutes. Let me talk about 23 as well. Okay. Okay, so do you remember that we have 32-bit, right? The first one is side bit, an 8-bit for exponent, and then 23 bits for the fraction. Okay. But if you see something, if you see the exponential, if they are all 0, okay, actually you don't calculate the value using this formula, okay? Don't use this formula, okay? Because if you see something all 0 over here, it is a special case, okay? If you see a floating point number with all 0 in the exponent part, it represents number 0, okay? So actually, if the side bit, it doesn't matter. If the side bit is 0 or 1, both of them represent 0, okay? Okay, so how about this one? Actually, you can use the IEEE 754 to represent the positive infinity and negative infinity as well. You can, right? So if you use all 1 over here, all 1 mean what? 255, right? If you see 255 over here, it represents infinity, okay? Not a true number that you calculate before using this formula, okay? So if you see 255 over here, or if you see 0 over here, you know that these are special number, and you can answer right away. In this case, the number is 0. It doesn't matter fraction, okay? The number here is 0. In this case, I remember for 0, this guy had to be 0 as well. So for positive infinity, the exponential had to be all 1, and the fraction is 0, okay? Negative infinity, the side bit had to be 1. All the bits here should be 1, and the fraction should be 0 over here, okay? And then sometime IEEE also use some pattern to indicate this is not a number, okay? Not a number. So if you have all 1 over here, okay, but the fraction is not 0, then this represents not a number, okay? Not the infinity, but not a number, okay? So just pay attention to these 5 special values in IEEE 754 for me, okay? So with that, I would like to stop the lecture over here. If you have any question, you can ask quickly, but I hope that is clear. Or you can wait until the next lecture on Wednesday, and I will answer your question. Okay. So
the highest exponent you can have is 254. Then, because
exactly.
as long
you're right. Exactly, William. Yes, exactly. Right. Yeah. Thank you so much, everybody, and hope to see you on Wednesday. Okay.
Okay. And NaN is what again? I forget. It is
not a number.